Why are statistical calculations needed in scientific projects? Suppose you like dogs and decided to do a project related to them. For example, compare the sizes of beagles, Cavalier King Charles Spaniels, French Bulldogs, miniature Schnauzers, and Shih Tzus to find out which of these dogs is the smallest. A beagle lived next door. You have long liked Cavalier King Charles Spaniels, and you had a book on their breeding at home, which your parents gave you as a child, and it also mentioned their size. You sometimes saw a French Bulldog at the playground. The size of miniature Schnauzers was found in an article describing the appearance of this breed in Germany. And your friend gave you the phone number of a unique Shih Tzu breeder. You can call and ask about their sizes. What do you think? Is it a good idea? Has everything been thought through? Not really. There are many questions about such a project, and we will address them all. Any research begins with thinking through the principles of collecting experimental data. At this stage, we will need an understanding of 4 terms: population, sample, representativeness, and randomization. In our example, the population is the size of all dogs of a given breed living, say, in the United States. This population has a population mean X. This is a very precise value. But in practice, it is almost always impossible to calculate the population mean. Therefore, we are forced to make a sample from this population, to take only those dogs that we can measure. And the skill of making the right sample is where the challenge lies. We need to make a sample that is representative. That is, it reflects all the key characteristics of the population. We can already catch a mistake in our project plan in this part. If we take the size of miniature Schnauzers from the German population, and the project is intended for the USA, it is quite likely that the size of German dogs will differ from that of American ones. Therefore, the sample of German miniature Schnauzers may not be representative of American ones. If small Shih Tzus breeders specifically breed smaller dogs, the average size of the dogs will be smaller and also not representative. And if you take information about Cavalier King Charles Spaniels from an old book, the breed sizes may likely have changed over the past 10 to 15 years. And if there is no access to the necessary information, it is worth abandoning such research. Local dogs, both neighbors and those you can meet on the street, might theoretically work, but we need to ensure that our sample is representative. What needs to be done for this? In this case, randomization will help, meaning a random but representative sample from the general population. Here we found several dogs of the suitable breed. You can't choose dogs based on the principle, this dog is cute, I'll measure it, but I won't measure this one because it's bitey. If there is a choice, it is best to use the lottery method. Mark all available dogs with numbers and then blindly draw as many numbers as the dogs you are willing to study. Or generate a series of random numbers and use it to select. Now you might ask, why bother with a lottery or random numbers? We have 3 dogs, let's measure them all. Here, we hit the second crucial point. 3 is the minimum sample size. It's way better if the sample size is 30 dogs, ideally 300 or more. But measuring all the dogs in the world isn't an option, so we'll have to choose. Regardless, for any statistical calculations, a sample can't just include one measurement. For example, you measured your neighbor's French Bulldog, and it's 13.5 inches tall. Then, at the park, you found a beagle measuring 12.9 inches. Does this mean the beagles are smaller than the French Bulldogs? Nope. Why? Because in biology there's this thing called variation. 2 living beings are rarely identical. There's only a certain probability that picking a random beagle will give an average height for the entire local beagle population. In statistics, probability is a numerical measure of how likely an event is to occur, expressed as a value from 0, impossible, to 1, certain. And probabilities have limitations in their range. For example, tossing a coin can land on heads or tails with a probability of 1/2. When you roll a die, it can land on a value from 1 to 6, each with a probability of 1/6. Similarly, the traits of living beings change only within certain limits. For example, the color of a dog's coat is determined by either the black pigment melanin, the yellow-orange pigment carotene, the absence of pigments, or their mixed combinations. But no dog with natural fur will be purple like an eggplant. In biology, dealing with probabilities is generally complex, Can you name any real biological event that occurs with zero probability? Or with a probability of 100%? Such probabilities are like finding a needle in a haystack. Even a purple-haired dog can be created in the lab using genetic engineering in theory. Fortunately, most biological researches aim for probabilities up to 95%. Let's try to show you visually how to eliminate randomness and achieve the coveted 95% confidence level. First, let's create a coordinate system where the x-axis represents the size of dogs at the withers, and the y-axis represents the number of dogs of that size. We plot the sizes of our dogs. We make a simple but incorrect conclusion that beagles are smaller than French bulldogs. But we don't stop there and make not 1, but 10 measurements, meaning we now have what is called a small sample, less than 30 observations. We enter these results into the graphs. What has changed? Now, instead of the results of one measurement, we can compare the average values for 10 measurements. The average x, denoted as x bar, equals the sum of all measured values of parameter x, in our case, the height of dogs at the withers, divided by the number of measurements. Statistical calculations are very convenient to perform in Microsoft Excel. Here is our initial data. These are the x values. Using the built-in function, we sum all these values from the first to the last. We have 10 measurements, so we divide the resulting sum by 10 and get the desired x average. We round to 1 decimal place. This is sufficient for our research. In our study, the average height of French bulldogs drops to 11.9 inches, while that of beagles rises to 13.9 inches. But our measurements still look strange. For example, for some reason, there are more French bulldogs with a height of 11.1 inches than 11.3 inches, and both graphs look somewhat curved. Such ugly results usually occur in two cases: if our sample is too small and is strongly affected by randomness, or if the measured characteristic is influenced by a factor that increases the frequency of extreme values and decreases the frequency of average values. For example, some dog breeds have dwarfism, anomalously increasing the number of very small representatives. In any case, to clarify the picture, there is nothing left but to take even more measurements. Let us increase the sample size to medium and take 30 measurements. What do we see? The range of height fluctuations has increased. New extreme values have appeared, very tall and noticeably short dogs. But at the same time, the average height has hardly changed. This is normal. The more dogs we measure, the more likely we are to randomly encounter taller and shorter ones. But while the range of height values may increase, the average value remains almost unchanged. And our chart begins to resemble a bell-shaped curve. And what happens if we make a large sample? For example, 300 measurements. In this case, almost all randomness disappears. The curve begins to resemble an inverted bell very accurately. Such a symmetrical curve is called a normal distribution. Most often, traits in biology have exactly this distribution. The asymmetry at the beginning of the study with a small sample turned out to be just a consequence of the small sample size, not dwarfism or other reasons. And the most pleasant thing is that such normal distribution curves, unlike individual measurements, can and should be used in statistical calculations. The behavior of variable quantities in large samples becomes predictable. This is almost as accurate and reliable a mathematical characteristic as the absolute values of the population. Now you can see that if the difference between two random measurements doesn't help much in finding the general average x, then the more measurements you have, the closer the average x gets to the general x. It's impossible to do an infinite number of studies, so the average x never reaches the big X in practice. But it can get close enough that more precise values might not be needed. The averages in medium-sized samples, from 30 to 300 measurements, are already relatively accurate. But even if the averages in two samples are noticeably different, from a mathematical statistics point of view, this is not enough to claim that the difference between the averages is statistically significant. Because if you look closely at data from a large sample, you can see some imperfections, deviations from ideal symmetry on normal distribution graphs. What if these deviations are not random, though? So now we will evaluate the spread of data and calculate the average error. and somewhere a mathematical statistician will breathe a sigh of relief. In our experiment, the dogs have different sizes, which means we observe a range of values. The range of values describes the parameter S, capital S. If all the dogs suddenly had exactly the same size, S would be 0. S, like the general X, is unattainable in practice and cannot be calculated, so in statistics, the standard deviation sigma is used instead. With an infinite number of studies, sigma tends to approach S. The standard deviation, sigma, shows how much the values are spread out relative to their mean, expected value. It is calculated using the following formula. Sigma is equal to the square root of the sum of the squares of the differences between each value, xi, and the mean value, xmean, divided by the number of measurements, n. Let's calculate the sigma using the example of the size variation of French bulldogs in a sample of 10 dogs. First, we calculate the difference between the size of each dog and the average size. Then, we square each of the differences. We sum up the squared differences. We divide it by the number of measurements. We take the square root and round it to 1 decimal place. That's it, sigma is found. Using the same principle, we will calculate the sigma for samples of 300 dogs. Sigma is a very useful parameter. Firstly, it predicts the spread of values. According to the 3 sigma rule, the probability that a random variable will take a value deviating from the expected value by more than 3 standard deviations does not exceed 0.28%, which is negligibly small. Secondly, knowing sigma, we can perform the simplest statistical calculation that adds scientific rigor to the research project. It allows us to calculate the standard error of the mean using the following formula. If the number of studies increases, the sigma remains almost unchanged. After all, it is not an error, but an indicator of data dispersion. However, the error of the mean tends to 0, and the reliability of the estimate increases. Knowing the standard error, we can specify the confidence interval for the population parameter x. As mentioned, its exact determination is impossible, but by calculating the standard error, we can say within which limits we can find this elusive parameter. The expression for calculating the confidence interval with a 95% confidence level looks like this. If you need a 99% probability, the critical value increases from 1.96 to 2.576. Confidence probability P is our degree of confidence that the population parameter x falls within the boundaries of the confidence interval with a probability of 95% or 99%. Suppose you prefer to see the glass as half empty rather than half full. In that case, you can choose the inverse value, the significance level alpha, also known as the degree of uncertainty. This is the probability that the population parameter x does not fall within the boundaries of the confidence interval with a probability of 5% or 1%. As you can see, when scientists say they are confident or not confident about something, it's not their opinion, but the result of meticulous mathematical calculations. Now let's apply this formula to our data and find the confidence interval for the population mean x with a 95% confidence level. First, we calculate the confidence interval for French bulldogs with a sample size of 300. We draw this segment on our coordinate system. Now we are 95% confident that the value of the population mean x lies somewhere within this segment. Using the same principle, we calculate the confidence interval for beagles. For beagles, after rounding the confidence interval values to 1 decimal place, the sample mean practically equals the population mean x. So we simply plot a point on the graph. The confidence intervals do not overlap, so we can say that on average, the height of French bulldogs is statistically significantly lower than that of beagles. And even if we had been lazy and taken a medium sample, the confidence intervals would have grown, but not overlapped. So, in the end, we captured the population x. Now it runs not across the entire x-axis, but only within the confidence interval. And we proved the statistical significance of the results for a 95% confidence level. The project goal is achieved. Hooray! What if we want to find out which reinforcement, positive or negative, is more effective for training dogs? Let's plan an experiment. Since its goal is to account for the influence of the factor, type of reinforcement on the trait, learning speed, we need to minimize the influence of all other factors. Ideally, we need to take at least 60 dogs from the same litter, raised in identical conditions, divide them into two groups, and conduct the experiment in ideal conditions, excluding the influence of weather, owner's personality, dog's mood, and everything else. In other words, ideally, we need a spherical situation in a vacuum, which is impossible to achieve. What we can do is minimize the differences between the dogs and rely on statistics, which are designed to distinguish randomness from patterns. We can take dogs of the same breed, such as Labrador retrievers, which are well trained to recognize certain scents. We can take dogs older than 1 year, and, if possible, only those that have already completed a basic training course. This is not an easy task, but it is doable if you gather a team of Labrador retriever owners who are willing to participate in the experiment. Then we will face another dilemma. Experiments in biology should be as humane as possible. No one will understand you correctly if you use kicking the dog as a method of negative reinforcement. But if you limit yourself to a disappointed voice as negative reinforcement, it will be acceptable. The model of our experiment will be as follows. We find 60 owners of Labrador retrievers who have completed a basic training course. They teach their dogs to bark upon detecting cinnamon sticks, provided that none of the dogs can recognize this scent before the experiment begins. A preliminary test with video recording is conducted to prove the dog's inexperience. Each dog is assigned a number, and the distribution into positive and negative reinforcement groups is done by lottery. Everyone uses identical tin cans to mask the scent, and mint and eucalyptus oil are used as the wrong scent. 30 owners in the experimental group use positive reinforcement, praising the dogs in a happy voice for each correct action but not reacting to failures. 30 owners in the control group use negative reinforcement, scolding the dogs in a disappointed voice for each mistake but not reacting to success. Training is conducted for 15 minutes daily at home to minimize unexpected factors. To analyze the impact of negative and positive reinforcement on scent recognition training in dogs, we can use the time taken to recognize the scent or the number of correct recognitions out of a certain number of attempts. Both parameters can be used, but we will use the time parameter for our hypothetical experiment for simplicity. Each owner records the training process, how much time it took, how many reinforcements were needed, and it's preferable to make a video report to check the experiment conditions. It's also important to ensure that owners in the negative training group do not scare the dogs, but only show their disappointment in case of failure. Now the experiment is ready, and we just need to accept any results. I understand that we all want positive training to be more effective than negative, but if it turns out otherwise, be honest and objective. Let's assume we have the following results. Now we can determine if the difference in mean values between two samples is reliable using the student's t-test. At this point, you might jump up and shout, "But we already compared the means using the confidence interval." To which I would reply, yes, but not quite. In the example of calculating the average size of dogs of two breeds, we needed to accurately determine the mean values and understand if they differ. The confidence interval shows the possible data spread and the statistical significance of the difference, but not the reliability. The devil is in the details. The student's t-test evaluates whether there is a statistically reliable difference between two samples. This is more suitable for our experiment, as we want to determine which reinforcement is more effective, rather than the average training time for a dog with positive or negative reinforcement. Usually, the results of the confidence interval and the t-test coincide, but if they differ, you need to use the t-test to assess reliability, while deeply pondering why the confidence interval says otherwise. So, quietly, children, let's get back to processing the results. Our data is quantitative, normally distributed, and the two samples are independent. They would be dependent if we took one group of dogs, first applied negative reinforcement, recorded the results, and then used positive reinforcement and recorded the results again. This approach wouldn't make sense because by the start of the second experiment, all the dogs would already recognize the smell of cinnamon. Therefore, in this case, we can confidently apply the formula for calculating the student's t-test as the difference between the mean values of the first and second samples, divided by the square root of the sum of the squared errors of the means of these samples. We also need to calculate the degrees of freedom, df, as the sum of the sizes of the first and second samples minus 2. We substitute our values into the formula. Don't worry, you only need to create such a long table once, and then you can use it as much as you want, inserting new initial data and slightly editing it for the new amount of data. Or, if you prefer, you can delegate this work to statistical calculation programs in the future. But for now, we are learning, and this is the best time to look inside the box and find out what magic drives these calculations. So, we get the t-test value and compare it with the critical value. Hooray! Our value is greater than the critical value. This means that the difference is significant and reflects a real pattern. Good triumphs. Positive reinforcement in dog training is statistically significantly more effective than negative reinforcement, at least for our made-up numbers. So far, we have analyzed traits that could be measured quantitatively. But what if we want to investigate qualitative differences? For example, how does the color of a dog's coat affect its flea infestation level? In this case, the trait we are studying is color, which seems impossible to measure in numbers. But actually, it can be done. In such cases, we can assign scores or categories to certain traits. For example, white dog, 0, red dog, 1, black dog, 2, spotted dog with small spots, 3, spotted dog with large spots, 4. Next, we conduct the study, keeping in mind the previous advice. Impartially make a representative sample from the general population of dogs differing in coat color, living under the most similar living conditions. For example, study all the dogs that come to the same dog park. As a result, we get the following distribution. For such data, even calculating the mean value is meaningless. Another method of statistical analysis, chi-square, will help here. Chi-square can and should be applied to samples that cannot be described by any function like the normal distribution, but can be represented as a so-called variational series. A variational series is an ordered or ranked sequence of data values. In our case, it is a ranked series of scores from 0 to 5 and the corresponding number of dogs with and without fleas for each score. Sometimes it is just impossible to gather a lot of data, and even more so to have the same number of measurements in 2 rows. You can still use the chi-square in such cases, but it gives the most accurate results when the number of observations is equal and there are more than 5 values for each score. We have the same amount of data, 30 here and there, and the number of values for each score in each subgroup except 1 is more than 5. The calculation and interpretation of the chi-square test results are still possible, as 5 is the minimum acceptable value. So, if you really do not want to chase fleas, we can stick with the data we have already collected, although ideally, we should increase the sample size of white dogs. The chi-square formula looks like this. N1 and N2 are the sizes of the 2 samples, and F sub I1 and F sub I2 are the number of objects possessing the ith trait in the first and second populations, respectively. Next, we create a table to calculate the chi-square for our data. While our calculations are nearing the finish line, let me tell you a bit more about confidence probability. We choose it ourselves. We can select 99%, 95%, or even 90%, and each of these probabilities has different critical values. Typically, for biological research, 95% is chosen, but if you are conducting medical or aerospace research, you may need a 99% probability. If you want to test the waters with your research, 90% might be sufficient. In the formula for calculating the number of degrees of freedom, K is the number of scores. In our case, it is 5. The calculated chi-square value in our case is less than the critical value, indicating no statistically significant difference between the two samples. Although there is a belief that light-colored dogs are usually more flea-ridden than dark-colored ones, it might be because fleas find it easier to play hide-and-seek in dark-colored dogs. Now, we have decided to study the gender structure of the local population of Doberman Pinschers. The results showed that the number of females is 33, while the number of males is 25. As always, it's tempting to rush to the conclusion that there are more females, but let's make sure the difference is statistically significant. For the calculations, we need to create a null hypothesis, which is a theoretical assumption we want to prove or disprove in the experiment. In our case, it is assumed that the ratio of females to males should be 1:1. This will be our null hypothesis. Let's create a table with the results. We apply the chi-square formula, which in this case is slightly different. Here, E is the observed empirical frequency, and T is the theoretical frequency. We perform the calculation. We choose the confidence probability again as 95%. In the formula, the degrees of freedom K is the number of classes. The critical value is greater than the calculated value. Therefore, the observed gender ratio with 95% probability does not differ from 1:1, even though the number of observed females is greater than the number of males. If you decide to get a dog, you want it to live as long as possible, right? You started to study the question, which dog's breed will bring you joy the longest? Comparing the numbers, it seemed to you that the larger the dog, the shorter its lifespan. By the way, in this example, the numbers are real, not made up. It turns out that we need to identify the relationship between two phenomena, the size of the dog and its lifespan. In this case, correlation analysis will help us. And here you might exclaim, "You are confusing us again, because we have been studying correlations all this time, and the t-test and chi-square serve this purpose." Don't worry, we'll sort it out now. Yes, the goals of the t-test, chi-square, and correlation analysis partly overlap, but the t-test and chi-square can only show the presence or absence of a relationship. Correlation analysis allows us to determine the strength and direction of the relationship. Whether one variable increases as the other increases, direct relationship, or decreases, inverse relationship. Dogs' weight and average lifespan are measured quantitatively and have a normal distribution. Therefore, the Pearson correlation coefficient, denoted as R, is suitable here. It is calculated using the formula R is equal to the sum of the products of the differences between each x value and the mean x, and the differences between each y value and the mean y, divided by the square root of the sum of the squares of the differences between each x value and the mean x, and the sum of the squares of the differences between each y value and the mean y. We perform the calculation for our data. The Pearson correlation coefficient can range from -1 to 1. If R equals 1, the correlation is direct and very strong. If R equals -1, the correlation is inverse and very strong. If R equals 0, there is no correlation. The phenomena are unrelated. We have found a fairly strong inverse correlation. To determine the reliability precisely, as always, we need to compare our coefficient with the critical value to ensure that the observed correlation is not random. We choose a 95% confidence level. In the formula for calculating the degrees of freedom, N is the number of pairs of observations. In this case, our calculated coefficient in absolute value is greater than the critical value. This indicates that the result is statistically significant. That is, the lighter the dog, the longer it lives. Who would have thought? Another idea for an experiment came to mind. How does the distance of a walk affect the number of times neighborhood dogs bark at you and your buddy? Distances can be expressed in numbers, but they do not have a normal distribution, so the Pearson criterion does not apply to them. In such cases, the Spearman criterion will help us. By the way, even if the data were in rank, it would also be suitable. The minimum number of values at which it starts working is 5 pairs of data, although getting 10 to 30 pairs of data is recommended. We, I'm sure, are lazy people, so if the minimum is 5, that's how many we'll measure. Let's assume we got the following results. Although the length of the walk and the number of barking dogs look like numbers, wipe your eyes, it is just an illusion. For calculating Spearman's correlation coefficient, we care not about the length in minutes and the barking in counts, but about how the ordered data series match each other. That is, how well their ranks coincide. Ordering data series by magnitude is called ranking in statistics. We need to rank each data series separately, that is, for the length of the walk and the number of barking, and assign them ranks. Let us do this. Note that Max and Sparky were barked at the same number of times, 5. In this case, we give them ranks equal to the average of their ordinal numbers. So, in our case, it is 3.5. Ideally, such generalizations should be as few as possible. In the end, we combine the results into a single table, but now correct with ranks. The correlation coefficient is calculated using the formula where x is the rank of the first variable in the pair, y is the rank of the second variable in the pair, and n is the number of pairs. Let's calculate our values using this formula. We choose a 95% confidence level, and the number of degrees of freedom is calculated using the same formula as the Pearson correlation coefficient. The critical value in this case is very large, approximately 0.878. We anxiously watch the growing columns of numbers. Will our calculated value be even higher? And now the numbers are almost at the finish line, just a couple of seconds, and yes, the calculated correlation coefficient turned out to be even higher, almost as close to 1 as possible. Our values are statistically significantly correlated. That is, the longer the walk, the more fresh dog news you'll hear. Can you imagine a project where the results can't be measured in numbers, not even in points? But it happens. There is a challenge where a plate of food is left in front of a dog, and the owner leaves to see if the dog eats the food while no one is watching. To make it more interesting for you, I watched recordings on YouTube, so the results will be real this time. The owner of the channel, Oringo, Ipe, and Makina Basenji Training, kindly permitted us to use her videos, so you can see an example of how funny this challenge looks in practice. The link to the video can be found in the description. The observation results can be recorded as either yes, ate, or no, didn't eat, or plus and minus, whichever you prefer. If the dog ate a small piece from the edge, thinking no one would notice, it was counted as ate. But if the dog only licked the food or held it in its mouth and put it back, yes, that happened too, it was counted as didn't eat. The goal of our experiment will be to see if the results differ when there is 1 dog in front of the plate versus 2. For calculations, we will create a 4-field table. Although the answers yes and no are not numerical by themselves, we can count the number of these answers and enter them into the table. The phi coefficient of association is calculated using this formula. Let's calculate the results. If the association coefficient is less than 0.1, it means there is no association. If it is between 0.1 and 0.3, there is an association, although weak. If it is between 0.3 and 0.5, the association is moderate. Greater than 0.5 indicates a strong association. In our case, we found a weak negative correlation. This means that if you want to leave a dog to guard your food, the chances of success are slightly higher if the dog is alone, rather than in the company of its playful friends. Finally, we decided to engage in a favorite activity of biologists, comparing and grouping objects, also known as clusters, based on the similarity of many of their characteristics. Phylogenetic trees are constructed this way. In this case, cluster analysis will help us. Cluster analysis determines similarity based on similarity or difference coefficients, for which there are different calculation methods. The choice of these calculation methods lies with the researcher, so we will choose one of the simplest methods, the difference coefficient based on the Pythagorean theorem. Yes, the very same one. Pythagoras knew the score. A squared plus b squared equals c squared. But what if we place our triangle in a coordinate system? In this case, the lengths of the legs can be determined using their projections on the coordinate axes. Since the laws of the plane and space are equivalent, adding another coordinate z doesn't fundamentally change the formula. In the case of multiple points, the formula will be as follows. But what do features have to do with it, you might ask? The thing is, you can work with any feature values just like with regular distances in a regular geometric space, or not so regular multidimensional space. The smaller the distance between 2 points in space, the closer they are. In cluster analysis, instead of points, we have objects, and instead of distance units, we have abstract units. The smaller the difference between two objects, the closer they are. Even the term that describes the degree of closeness between objects is also called distance. To understand how this works, let's look at the differences in pet preferences in countries where people particularly love having pets. In North and South America, USA, Brazil, Argentina, Canada, Europe, France, UK, Germany, Italy, Asia, Japan, China, and Australia. We'll have a wide variety of pets, from familiar dogs and cats to exotic aquariums, birds, rabbits and rodents, horses, and even snakes. We will rely on statistical data showing the number of pets per 100 people in each country. Cluster analysis will help us find kindred spirits, countries where people have similar ideas about the ideal pet. Does this seem not entirely scientific to you? But who said it was impossible? Statistics is just a tool for data processing, and you can apply it to anything. For example, there are real studies that examine how many scientists enjoy licking stones, or how many hairs grow in each nostril of a person. And this is not a joke. These works have even been awarded the Ig Nobel Prize, an award for the most unusual and amusing scientific achievements. My task is to show you how statistics can be useful even in the most unexpected situations. So let's continue. To illustrate the calculation process, let's take the first two countries and compute the Euclidean distance between them. In cluster analysis, the obtained distance by itself means nothing. It only makes sense when we compare a set of objects with each other. Let's do this for our example by creating a distance matrix. This matrix shows distances for all possible pair comparisons, but don't freak out too much. There's a lot of fluff here. Look, there are zeros along the diagonal. Guess why? On either side of this diagonal, the numbers are symmetric. We don't need duplicate and empty values, so we remove them and get a much simpler matrix. This matrix already contains the answer to our question if you look closely, but we'll do even better. We'll draw a dendrogram, and you won't need to look closely. Everything will be perfectly visible from afar and at once. To draw the dendrogram, we need cluster analysis itself. There are many ways to conduct it, but most are so labor-intensive that it's hard to do without special software for statistical data processing. But my task is to explain the principle of cluster analysis, so we'll use the simplest method, the nearest neighbor method. Unfortunately, it's not the most accurate. More accurate results are given by the pair group weighted average method and Ward's method. But for government work, for the first steps in statistics, it will do. For this method, we find the minimum distance. In our table, it's 3.1, Canada and Japan. We start drawing the dendrogram. Next, we find the next smallest distance, which is 4.4, UK and Japan. However, Japan is already merged with Canada, so we add it to that cluster. The next smallest distance is 4.8 between the UK and Canada, as well as between Italy and Australia. The UK and Canada are already in a cluster at a smaller distance, so we skip this information. Australia and Italy haven't joined any group yet, so we cluster them separately. Next is 5.3, Japan and France. Japan is already in one of the clusters, so we add France to that cluster. The next smallest distance is 6.5, France and Canada. Since they are already in clusters, we skip it. Then, at 6.8, we find Canada and Germany. We add Germany to the cluster with Canada. Now, at 6.9, we find France and China. We add China to the cluster with France. The distances 7 and 7.8 involve repeating countries, so we skip them. The next minimum distance is 9.1, Brazil and Australia. We already had a cluster with Australia and Italy, so we add Brazil to it. We skip the following distances again because these countries are already in clusters. At 12.9, we have Argentina and the UK and Argentina and Canada. We add Argentina to the cluster with the UK and Canada. At 14.7, we have Germany and the USA, so we add the USA to the cluster with Germany. At 15, we have Argentina and Japan, but we skip it. At 15.1, we have Australia and the USA. This is the most interesting part. We already had a cluster with Australia, Italy, and Brazil. Now we can merge the whole cluster with the USA. All countries are united. Cluster analysis is complete. Now we just need to understand what causes the observed relationships. Any ideas? Now you know the basics of statistics. One last piece of advice. Before choosing any statistical method, always think if your data and tasks fit the chosen method. If you have a nagging doubt, it's probably right. There are many methods of statistical data processing, and for reliability, always choose the right one. You can be 100% sure of that. Good luck with your science projects.